Good afternoon. Welcome to Best Paper Session number 2, paper number 3. As a courtesy reminder for all of you, please silence your cell phones during the presentations. Also wanted to remind you that these sessions will be recorded. If you do need to leave, I would encourage you not to leave during the presentation, but if you do need to leave during the presentation, please be aware that there's a camera in the back, so please avoid that if you can, and please use the 2 exits at the rear of the auditorium. Also, as a reminder, all conference registrants this year are available to obtain CEU credits for paper presentations, so make sure that you have been scanned in if you need CEU credits for this session. Our third paper is from our training subcommittee. It's called Attention and Engagement in Virtual Environments, Measuring the Unobservable. Our presenter is Dr. Benjamin Bell. He is president of EduWorks, where he leads simulation, human-machine interaction, and decision support development. He is an adjunct professor with Embry-Riddle University, holds a PhD from Northwestern, and is a graduate of Pennsylvania University. Please welcome Mr. Bell. Dr. Bell, sorry.
Good afternoon. I'm Benjamin Bell from EduWorks, and this late in the week and this late in the day, I tend to start leaning on any flat surface. But the last presentation, there was so much talk about posture that I'm kind of self-conscious about it, so please don't judge me. The work that I'll be talking about was done in collaboration with USC's Institute for Creative Technologies, Dr. Ben Nye, and with the Air Force Research Laboratory, Dr. Wink Bennett, and with my colleague, Elaine Kelsey. Oh, I just clicked on my slide. Thank you, whoever whispered that. There we go. So before I jump into the work, if you could indulge me, I want to do a short thought experiment. And in the next slide, you'll see a series of images of people. And what I'd like you to think about is how engaged do you think each person is in these images? And actually, I'm not asking you to think about how engaged they are so much as how would you go about trying to measure how engaged they are? So let's roll the tape. So you may have seen some of the people who were smiling, some were waving their arms around, and so you might think, hey, they might be pretty engaged. Others had, like the warfighters, had kind of their game face on, so that's a little harder to tell. And you might have also noticed in some of the pictures there were multiple people. So that probably escalates the challenge level in estimating engagement. So that gets us thinking about engagement, but it also begs the question of why do we care? What's really at stake here? And the short answer is training. So in the research that we cite in the paper, engagement is a prominent factor in both learning outcomes and learning retention. And good instructors know this, and they will bring a student back into a more engaged state if they notice and if they have the bandwidth to do that. But that kind of assessment is largely beyond the reach of automated instructional systems. And that's really what this work is about. It's about helping to develop automated metrics to capture that engagement level. So that's the why, and to help answer the how, I've made this nifty little roadmap with the blue boxes, and we'll be referring back to that as we go. I'll talk about a general model of engagement that we synthesized from the research and how we applied that as a basis for adaptive learning. But then talk about an exploration we did of using machine learning techniques to learn to associate patterns of user activity with levels of engagement, and then how we applied those models to adaptive learning. Finally, I'll talk about a formative evaluation that we did and the dashboards that we built to support that formative evaluation. The context for this work is pilot training transformation, PTT. At the time, it was Pilot Training Next, PTN. It's an Air Force program you may have heard about that is using VR and PC-based simulation in lieu of legacy ground-based training devices. And it's a good use case for our work because in the initial years of PTN, the Air Force wanted to collect a lot of data because everyone needed to be confident that students coming through that pipeline had the requisite proficiencies. And they're still collecting a lot of data. And so that's good for us. Another thing that makes it a good use case is that part of the vision is that one instructor can supervise multiple students who are simultaneously flying in different scenarios. So if you think back to those images of when there's multiple people, it's probably a little harder to detect loss of engagement or a lapse in engagement. So back to the roadmap here. We started with a generic model, a general model of engagement, and we synthesized this from 9 engagement models from the research literature. But we tuned it to have more of an aviation focus, where we emphasized monitoring and event response. So monitoring in this case might be maintaining straight and level flight, or an event response could be maneuvering to avoid a hazard. The model has 3 top-level categories: performance, efficiency, and responsiveness, which I call out because they'll come back again, and you'll see them appear in the dashboard that we built for the formative evaluation. For adaptive learning, we also synthesized a model from the research. And the adaptive learning model, the purpose of it is to understand what kind of engagement lapse was detected and to map that into the appropriate adaptive intervention. And so we wanted to be able to describe the adaptation in a way that would help cue an instructor about how to respond when a student had a lapse of engagement. So this kind of brings us into the core research element of the work. And this was to explore machine learning techniques and how those models might help us to associate patterns of activity with user engagement. So we created the general model that I showed you a diagram of. It's not a machine learning model, but it's a baseline model that we could use to measure the machine learning model performance against. And we used 2 well-known machine learning techniques: support vector machine and hidden Markov models. So machine learning, it's a pretty compelling paradigm, and it's potentially very powerful, but most techniques require a lot of data. So to generate the machine learning training data, we recruited pilots from local flying clubs. We had 36 subjects. And we built our own PTT testbed. And our testbeds ran the exact same software, the same PTT scenarios, and the same VR headset. So we didn't have the T6 seat, and we didn't have the rudder pedals or the stick and throttle, but everything else was functionally the same. And we had each subject fly a set of PTT scenarios that we selected to give a good cross-section of duration and challenge level. But then we had to figure out, well, what does it mean for there to be a lapse in engagement? And in the literature of aviation mishaps attributable to loss of situational awareness, boredom and distraction are two very prominent factors. So we use distraction and boredom as proxies for disengagement. During each subject's run, the experimenter would timestamp low intensity and high intensity portions of the scenario to help the model understand workload as it was learning to detect boredom. For distraction, we actually had the experimenter at fixed points essentially interrupt the subject with questions like, so what got you into flying? Or, what's your most memorable flight? So we used that data set to train the models, and before we could proceed, we had to kind of vector check the model predictions. And we used standard machine learning classifier metrics that you see listed here. But the data set was very asymmetric, and what I mean by that is that we expect that usually a subject is not going to be bored or distracted. Like in the room now, right? Okay. But because of the asymmetry of the data set, we used what's called an F1 score, which helps measure the model's propensity towards both false negatives and false positives. So using those metrics, we derived the scores that you see here in the table. And there's no real universal threshold that says this is a good F1 score, but the closer to 1.0 you get, the better. So we looked at the HMM model, and that gave us enough confidence to proceed with the work. We felt that level was high enough so that the model would be able to tag actual instances of lapsed engagement. So one important reason why you would want to detect an engagement lapse is that presumably you would then want to do something about it. So we also use the model to recommend adaptive interventions to an instructor. And the adaptive instructional model used the general model of engagement that I described before in those three categories: performance, responsiveness, and efficiency, and then used the machine learning model to provide deeper context in recommending what it thought would be the appropriate intervention. And it comes out looking something like this. This diagram is not the actual model because the search space of the model is very large, and it's hard to distill into a diagram. But this diagram does capture the key dynamics of how the model is operating. So back to our roadmap. Before we could do a formative evaluation, we had to create some visualizations. So we created two dashboards. The first dashboard we call the instructor operator view. I mean, honestly, I don't think an instructor would go anywhere near this dashboard, but it helped the development team really. So I'll tell you a little bit about these gauges. So the three needle gauges on the right, those are the three dimensions of the general model that we talked about: responsiveness, efficiency, and performance. On the left is the engagement needle, and this is what the machine learning model is calculating. Down below, these are every single time Omega flags an event. It displays it here, explaining the kind of engagement lapse it's detected, and also the values of each of those metrics at the time. For the instructor, though, we put together a notional tablet-style interface where we preserve those four needle gauges, but we only display the most recent event that Omega's detected, along with the recommendation description so that the instructor knows what's going on, and Omega also provides some example feedback to give to a student. So to actually do the formative evaluation, we created videos, and what you're seeing is on the left, this is the output from the simulator, from the PTT engine. And in these PTT scenarios, you see these virtual gates hovering in the air, and the students have to navigate through those waypoints. What you're seeing on the right is that tablet interface that I showed you in the dashboard. And so you'll see alerts pop up from Omega. And those needles that look like they're bouncing around, the engagement, Omega's looking not only at the actual value of engagement as it's calculating it, but also the trend, and even the abruptness of the trend. So it's possible that the needle could be in the yellow to green area, but still be flagged as an engagement lapse. And conversely, the needle could be bouncing around in the red to yellow range and not trigger an event. So this is the data that the instructors were asked to look at. For our formative evaluation, we had 2 civilian CFIs, and we had 1 reserve F-16 pilot with instructor experience. And they each looked at 5 of these recorded scenarios. These recordings came from the initial 36 flying club pilots that we used to collect the machine learning training data set. And what we were interested in from the instructors was their assessment of how well does Omega detect engagement lapses, and what do you think of Omega's recommendations for what to do about it? So we used standard ease of use expected benefit metrics. Omega scored very high with ease of use, and for expected benefit, Omega was positive. I would say like just barely positive, but it was on the right side of that pivot point. And the most common feedback we got had more to do with Omega's recommendations than with how Omega was detecting engagement lapses. And so instructors thought that Omega's recommendations were too frequent and too lengthy and too vague. Other than that, pretty good. And they said that we would generally wait and see before giving feedback. And instructors said that their feedback has more brevity and is much more specific to the task. So we kind of characterize their heuristics as settle in, give the student time, spread out, keep your feedback more, allow more time to elapse in between, and then back off. So if a student, for example, is approaching a maneuver, let them get through the maneuver. So on the positive side, the instructors agreed that Omega was very good at detecting engagement lapses. They had pretty good confidence that if Omega said there was an engagement lapse, that something was going on that the instructors should have a look at. So the bottom line on the detection side is that we think we had pretty promising early results with Omega as a disengagement detector. So, but in terms of Omega's feedback, they likened Omega to a brand new CFI who just can't stop talking, and then eventually learns to sit back. The instructors also said the feedback should be specific, and this was sort of interesting because Omega is designed as a service, that doesn't need to know about what's happening in a scenario. So Omega's feedback is very much about engagement, work harder or focus or this or that. And the instructors said that they didn't think that would be effective, that it really has to be contextualized. So this suggests a couple of research directions that this could go. So one, and you sort of picked up from our formative evaluation feedback, that we have to think more about how Omega is timing its feedback and how frequently we want to give feedback. But an intriguing other direction to go is that Omega could be a service that provides feedback directly to the student as mediated by whatever training system the student is working in. And one advantage there is that the organic training system that the student is working in knows a lot more about what's happening in the scenario than Omega is designed to know. So that would give us a conduit for making that feedback more specific to the context. So I would say overall, I mean, if you think of the crawl, walk, run metaphor, we were sort of like cautiously optimistic about the results with, that had to do with Omega's ability to detect lapses in engagement. And we think that it's applicable in a broad diversity of training applications. So obviously there's a lot of work to be done in how Omega responds to that. And so stay tuned for that. And before I close, I want to thank Jimmy and Mark for running the session. And I especially want to thank Bob Wallace, who was my bird dog, who was a great help in getting this presentation ready. Thanks for your attention and standing by for your questions. That's a great question. The whole genesis of this work goes back to 2017 to an Air Force SBIR topic, where the application they had in mind was early career airman training, where they have to pour through volumes and volumes of kind of dry technical material. And so the vision there is to use engagement detection to understand how good the training is and where do we need to make changes. In this project, we didn't address that, but I just wanted to share that that was kind of the genesis of the whole effort.
So, if I understand this right, so using the Omega systems, using machine learning algorithm to understand different features and traits of engagement or non-engagement. I don't know, did you mention specifically what are those key parameters that the system is looking for? Is it gaze, peopleometry, body posture? What's that?
We limited the data stream to the events that were being pumped out by the underlying simulator engine, which sends out a lot of data. PTT as a program collects biometric data as well. That we didn't use that. We also didn't use, so the headsets that PTT uses collects eye tracking data. Another data source we didn't take advantage of. So all those, like the more the better, but for this work, it was just the event stream from the simulator. Yeah, I think it would add a lot of context, and we just didn't because our customer didn't let us.
I'm just curious, mostly on the, because you could take that and turn around, especially for students, to see stress levels with biometrics with responsive times.
Yeah, and personally, I would like to make use of the eye tracking data. A lot of other research on detecting engagement makes use of, has cameras on the monitors and tries to collect eye tracking.